Oh, hi. I've been thinking about the psychometric function, and some of the previous videos that we did using Python, PsychoPy programming, but mainly Python, is we built up an idea of the psychometric function from first principles, from scratch really, and we did a method of constant stimuli, I think, pretend experiment. But upon reflection, I think we need to include a couple of other terms or a couple of other ideas when we start to model or really delve into using or, manipulating the psychometric functions as we will expect to get out of our real life psychometric experiments. Okay, so that's what I want to do today, is basically take us from the theoretical psychometric function into a little bit more of an applied understanding of how we should start to build or model our psychometric functions. So single video. I'm going to try and keep it quite short, but historically I haven't been able to do that too well. And it'll be a bit of whiteboard and then a bit of Python programming afterwards. Okay, so here is the whiteboard. I can see myself on that screen. Today's date is the 3rd of the 12th, 21. Merry Christmas if you're that way inclined. Now, let's have a think about the psychometric function. When we plot the psychometric function, or the easiest way to think about this psychometric function is we have on the y-axis here we have percent correct, and on the x-axis here we have stimulus intensity. Stimulus intensity. Now, and the understanding here, our understanding here is that if we have a very, say, it's doing an auditory psychophysics experiment. If the stimulus is very loud, the subject is going to be able to detect that at 100% correct. Okay, so it should be somewhere here where it's very loud. Let's just make this 100 decibels. It's very loud if it is 100 decibels. And they're at 100% correct. Okay, but as we turn down the volume, they're going to get it correct most often than not. More often than not, sorry. Keep turning it down, keep turning it down, keep turning it down, keep turning it down until it's basically off. And then we know that they should get 0% correct. Okay, so we were then able to previously say, okay, this is actually a sigmoid function, and that we know that we can describe this sigmoid with a cumulative distribution function. And in the previous experiment, videos, we used a Gaussian, right? A Gaussian CDF in SciPy, I think it was. Okay, a Gaussian. And we said, hey, look, we don't care if it's symmetrical or asymmetrical. We're just going to use a Gaussian cumulative distribution function. Right, but this is not what we would expect to see when we look at the data from a real-life experiment. I'll show you why. Okay, we're going to come back to this figure, if I remember to. Let's go down. Right, let's do a psychophysics experiment, okay? And we're going to do what we call a 2 alternate force choice task. So this is where your subject has to choose between option 1 and option 2. Okay. In this case, we're going to do a an orientation discrimination task. Okay. So orientation discrimination. Okay. And what we're going to do is we're going to do an animal experiment. We're going to use mice. What we're going to do is we're going to have an arena, quite a large arena, where it's a Y shape, okay? And we'll have a bit here. And the interesting thing with this arena is it's filled with water, okay? And halfway down this back end here, we'll have a barrier or a divider. Now, this barrier or divider, it's opaque, so you can't see left to right, okay? And what we do is we essentially put a mouse in at this end here, okay? So there's the tail, so we can see the mouse is pointing that way. And the mouse can swim, okay, either to the left, okay, or to the right, okay? But as soon as they have gone past the edge of this barrier here, okay, they've made their decision, okay? That's the rule. Now, what are we going to train them up to do? Well, in this experiment, it's an orientation discrimination task. And so at the end of this arena, we're going to have 2 computer monitors, Okay, so they can see the computer monitors. And what we've done is we're going to train the mouse up to detect a vertically presented visual grating. Okay. We're not going to go through how we do that. We're just going to say, hey, look, we've trained a mouse up sufficiently well such that they will be able to go, oh, that vertical grating is on the left-hand side. I need to swim to the left-hand side, okay? Now, just under the surface of the water, we have a platform, okay, a plastic platform that they can't see, but it sits just under the surface of the water. Okay, and that's their rescue platform. Once they reach that, they'll jump there, they'll start cleaning themselves. You know, we can then go gently pick up the mouse and put it back into its home cage, and then we do the next mouse and we can cycle through a lot of mice quite quickly. Okay, so the point here is that if they choose the vertical grating, the screen or the side with the vertical grating, that's correct. You know, if they swim past this decision line to the left-hand side, they may go back out and go this side, but their initial response was to go left to that side. So that's how we're going to say it's a correct. But if they swim to the correct side, well done, that's correct. Now, this vertical grating can be presented either to the left, okay, or to the right hand side, and that's going to be pseudo-randomized, okay? Now, hopefully this experiment should make sense. Okay, so the mouse is correct when it goes to the vertical grating. So what are we going to test for? Well, what we're going to test for is the following. It's an orientation discrimination. So we're going to have our test stimulus, which is the vertical grating, but we're going to compare that or versus that to our alternate stimulus, which can be a horizontal grating. Same spatial frequency, same contrast. We're not asking a contrast sensitivity experiment. Okay, this is just a simple orientation discrimination. So if we say that the test is 90 degrees in orientation, okay, and the alternate stimulus is 0 degrees in orientation, okay, to our mind, this should be quite easy to the mouse, shouldn't it? They should go, right, well, hang on. This is the one that's going to have the platform. That's the reward side, the correct side. And so I'm going to swim towards this side when compared to this one, which looks totally different. It's 90 degrees different, okay? So this should be easy. Not cognitively demanding, okay? And so therefore, we would expect them to get 100% correct. Okay, so if the vertical grating is presented on the left, they're going to swim to the left. If the vertical grating is presented to the right, well, they're going to swim to the right and not swim to the horizontal grating, which is presented on the other side. Okay, right. Well, let's change the orientation difference, or the delta ori. Okay, so d ori, delta orientation, equals 90 degrees. D just stands for delta, okay? Now, again, we're going to have 90 here. Again, this could be presented on the left or on the right side of the screen. I'm just putting it on the left just to make it easy for us to follow. And what we're going to do is we're going to have some trials where it's not going to be 0 degrees anymore, but, you know, we might want to give it 45. Now, what I've done in my experiments previously is I've put it at 10 degree differences, okay? So this would be a 45. In some other trials, we will leave the 90 degrees as it is. Again, can be presented left or right. So 90 degrees, bump, 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 bump. And we might do something like at 10 degrees, for instance. So this is going to be quite difficult. So you can see the task is getting a little bit harder now. So d ori, sorry, that's a d, equals 10. D ori equals 45. Okay, and then what we can do is we can actually do the hardest test, okay, where we have 90 degrees versus, you guessed it, 90 degrees. So here our d ori equals 0. Right, so hang on. If we have the left and the right screen both showing 90 degrees, only one of them has the platform, okay? And this is going to be the hardest test that they will get. to do, hardest. In fact, the mouse is going to be guessing. They're just going to guess because we can't, even as humans, we can't tell the difference between the two. We don't know where the platform is. And so we were just going to have to guess. Okay, so this is a guess. Now, because there's a 1 in 2 choice, so you've got option 1 versus option 2, they will be correct at 50% of the time. Okay, so 1 in 2 will be correct. So I think you might be able to see where our issue is now. Let's go back to our first psychometric function. We said, well, hang on. Ein Minuten bitte, as the Germans would say. Okay. We were expecting them to go down to 0% correct when they couldn't detect the stimulus. But in our 2 alternate forced choice task, we will never get 0%, or we will expect to never get 0%. Rather, we would expect to min out, okay, at chance, at 50%. Okay? And so the animals can't see the stimulus, okay, but they're still going to get 1 and 2 correct. Now, there should be no change in this top bit, okay? They should still get 100% correct at the top, okay? And so you can see here is the issue that we face. Okay? Our psychometric function, when we build it in Python, it has to take into account, now I think this is called lambda, or it's called gamma. Okay, I'll double check that when we go into the Python programming. Okay. So we're going to have some issues here, right, when we build our psychometric function. So first thing is we have to figure out, well, how are we going to take into account the guess rate? I'll give you another thing that we're going to be looking at in the next thing as well. Our mouse is never going to get 100% correct. We're going to have a lapse rate. And ideally, this is going to be less than 5%. So the lapse rate means that even if we make it the simplest task possible, right, the animal or your subject is still just going to get it wrong maybe 5% of the times. They just make an error. Okay, no one's perfect. Some people do try to be. I mean, I think I'd like to get close. But in all seriousness, we will also need to change our cumulative distribution functions, okay, to incorporate the lapse rate. I hope this made sense, okay? If not, go back to the start and see how we've built it up from scratch. I'm now going to go into into Python, excuse me, and we'll get cracking on a very straightforward approach to modifying our psychometric functions. I'll see you. Okay, so now we are looking at the programming side of things. Okay, so I've opened up my Visual Studio Code. If you use Anaconda, or if you use Spider, or if you use Atom or Notebook, it doesn't matter. Just open up and make sure that your editor is working and that you've got access to your Python libraries and that you're ready to get cracking, basically. Okay, now I'm going to look to the left a little bit because that's where my monitor is that I'm capturing, and so I might be jostling back and forth a little bit, so I'm not trying to be rude. I'm just looking at where I'm programming. Okay, so let's have a look here. Let's put a doc string right at the start and we'll remind ourselves what we need to do. The psychometric function needs to be modified. And we had the guess rate. Now, remember, for the 1 in 2 alternate forced choice task, even when the stimulus was very difficult, the most difficult, we're still running a 50% correct rate or guess rate. So that's going to be 50%, but we need to put it into a decimal, so that's going to be 0.5. And the other thing that we had, we called that gamma. Okay, so that is gamma. And then we also had what we called the lapse rate, okay? And that was even when it was the simplest possible. Excuse me. They're still going to get it wrong some number of times, some percentage of times. I think the sort of the formal definition is it's the stimulus independent error rate, Okay, that sounds a little bit more, but you know, you're going to have a number of errors regardless. That's independent of the stimulus. Doesn't matter. Okay, so we're going to say 5%. Okay, oh sorry, 5%, I'm jumping the gun a little bit, which in decimals will equal 0.05, and this is lambda. Okay, now, be careful if you want to name your variable lambda, because remember, lambda is a special function in Python, and you will come into trouble if you try and write lambda. Okay, so you'll see how we get around that. Sneaky get around. Okay, we're going to use a Gaussian cumulative distribution function from our SciPy. SciPy.stats library. All right, so let's import some things. We want, so this is going to be my flavor of opening a, of importing stuff. So if you have your standard boilerplate, so very common things that you always bring in, hey, bring them in and play with them as you need to. You'll see what I bring in most often. So I want to import OS, not import. Import OS. I want to from datetime. Oh, my spelling is really bad. Import datetime. It's going to be fun. It's going to be long. We want NumPy. Import NumPy as MP. We want the SciPy. So from SciPy.stats, import norm. And we also want to plot. So import matplotlib.py plot as plt. This should get us going right at the start. Now, let's clear the output of your terminal. Terminal. Good heavens. It's my day off today and I just can't spell for muck. Right, so os.system. What we want to do is, you see all this stuff down here. You might not be able to see it, but you see all this muck down here. Okay. Every time we run our program, we want to clear it out. So we start afresh. The errors that we do get are the errors that are most recent. Now, I've spelt that wrong. Once again, how is this even possible? Okay. We want to pass CLS if the operating system name is NT. Else, if it's not NT, we're going to pass clear. Okay, then we're going to print out under that, we're okay to go. Dear Visual Studio Code. We'll run that, we'll see if we clear everything up, and it runs. Okay. Invalid syntax. Okay, let's see what happens. Okay. There we go, we're down here now. Right. And try it a third time. And okay, good. Everything's fine. What I like to do, however, is not just print OK, but rather I like to print current date. What we'll do is datetime.now, format time, and what we want to do is we want to print the year, the month, and the date. Now we do it backwards. Why do we do it backwards? It's because when we need to order our folders, if you've got lots of experiments, you want to order them by date. By doing it back to front, when you sort ascending or descending, you'll be able to sort it appropriately by putting the year first. Now, we've got this one needs to be done, and then that. I don't like the help. Invalid syntax. What have I done wrong? Open, close, open, close. strf time. Percent year, month, date. What have I done wrong? Hang on. Okay, what I did. You see how I had the double apostrophes on the outside here? You need to make sure that you have just a single apostrophe inside the string format time here. Okay. And the other thing is we want uppercase Y, lowercase m, and lowercase d, and then that will give us the year, the month, not the minute, and the date. And the day, not the date. Okay, so you see this is working fine now. Right. We will need to now declare some variables. Okay, let's give us some space, bring this up. Okay, we will want... So in our model, we're going to need an average or a 50% correct, okay? And we're also going to need a standard deviation. Now, if that doesn't make any sense to you, I suggest you pause this video here. You look for my psychometric function videos and the series of videos that we've built the psychometric functions from scratch. Have a look at that. We pull it apart. We build it from scratch. Once you get your head around that, come back here and then follow along. We're sitting at some number of minutes. I'll see you when you come back, all right? So we need to do the mu, okay? And remember, our orientation stimulus is going to be between 0 and 95. Sorry, 0 and 90. So let's just chuck our average, or our 50% mark, somewhere between that. So we'll put it at, 45, okay? Now we also need the slope of the psychometric function about the median, the mean, okay? And so we'll say it's about 10, okay? Now, we also need to get the guess rate. Remember, this is gamma, okay? So we'll call it gamma. And what did we say the guess rate was before? We said we're expecting them to get 50% correct, even when, the stimulus are both at, the delta orientation is at 0. So it's vertical and vertical. Excuse me, I'm getting very emotional here. It's very exciting. So gamma is going to be 50%. Now, for a 2 alternate force choice task, they've got a 1 in 2 chance of getting it right. So it's a 50%. If you're designing a 1 in 3 alternate force choice task, they're going to get it correct 1 in 3 times. And so your guess rate's going to go down to 33.33%. Okay, so the guess rate is going to be dependent on the design of your experiment. We're doing a 2 alternate force choice test here. 1 in 2, 50%. Okay, now we need the lapse rate. Okay, remember this is the stimulus independent error rate. So even when it's the simplest imaginable, your subject is still going to be a dunder clunker in the head and get it wrong. I remember when I was doing my experiments, experiments for Dr. Michael Tan at the University of Western Australia. In the last lot, it was quite simple. We were building psychometric functions. It was the last simplest one, and I think I pushed the second interval, and it was the first, and I just threw my head back, and I went, ah! And I looked back, and there was the professor of psychology, Jeff Hammond, was there. I said, I fucked it. Part of the language. So even humans have a lapse rate. It was a really boring experiment. So we need to call this something. We're going to call it lambda, but we can't use the word lambda because that's a special function. So we're just going to underscore halfway through it. And we want this to be 0.05. So we're expecting to be about 5%, 5% error. Regardless, so that's something that we can't change. It's just, your subjects aren't perfect. Okay, so that should be our variables for now. Now, what do we want to build? We want to build a psychometric function. So that's going to need an x-axis and a y-axis. So the x-axis is going to be build the x-axis, and this is stimulus orientation between 0 to 90. So let's just go stim x equals numpy.arange 0 to 95. Now remember, we include the lower value here. We do not include the upper bound, okay? And that's what it says here. It includes the start value, but does not include the stop value. That's why we've gone up to 95 and we haven't stopped at 90. Why have we gone to 95? It's because our interval or step value, which we can see here, our step is going to be 5. We're going to put in a 5 degree. Why do I say degrees? Because remember, it's an orientation in degrees. So 0 to 95 in 5. Now, just to prove to us that we've done this correctly, we'll print this out. Stim x. Okay, so hopefully we should return a numpy array between 0 and 90. What do we get? Is it working? Have I done something wrong? Did I not push that button correctly? There we go. Okay, so here we go. It's gone between 0 and 90. Okay, so it's worked fine. Okay, Oh, there it goes. All right, so maybe it was just a bit delayed. Good. We don't need to print this out again. So now we want to build the y-axis, which is going to be the percentage correct. Okay, so y-axis, percentage correct. Are we still recording? We are at 11 minutes, almost 12 minutes now. Okay, so we want the model probability. Now this is not good. Oh, hang on, no, we'll do this slightly differently. We'll do probability correct. And this is going to be our... We need the NumPy, the SciPy module. So normal distribution. We want the cumulative distribution function. And this is going to require the values of the x-axis. So that will be the stim x. We need to pass it the average, which is going to be our mu value, which remember it's going to be that 45. And then we also need to pass it the standard deviation, which is going to be the SD value. Okay, so now, let's start plotting things. Now, if you want to clean up your code and put everything into functions, please do that. That is going to be an excellent move for you to do. We're just running a single line, single sheet here. Okay, so plot. I'm not going to do any subplots or figure axis generation here. We need our x-axis, and we need our y-axis. Now, our color, we're going to make this red. We're going to make our line width 2 points. We're going to make our marker x's. X marks the spot. We're going to make our line style. We're going to do some dashes. What else have I forgotten? No, bugger. We'll have a look. We'll see what we come out with. Now, plot dot. Let's limit our x-axis to 90. Let's give our x-axis a name, x label, and this is going to be d-ori, because remember, delta orientation. Do the same for the y. Plot dot y limbs 0 to 1.05. Oh, not 10, 1.05. Get out of there, please. Now, you'll see why I've gone over the 1, because remember, we would expect to have 100% correct, but I've just gone over a little bit more because we're going to put a horizontal line there just to really define things, make things look a little bit cuter. Okay, and plot dot y label. Now, you're going to have to change things if your professor wants something different, or if you yourself want something different. Correct. And we'll put our units there. I think we can probably do now a plot dot axes, horizontal line. We want a horizontal line to appear at 50%. We want our line style to be also a dash, but we don't want it to be such a big line, so we'll make the line width say 0.5. Okay, and we want the color, although the color is spelt wrong. Thanks, America. We'll make it a grey color. Now, these three values here, 0.5, 0.5, 0.5, is basically saying we want 0.5 or 50% in the red channel, 50% in the green channel, 50% in the blue channel, so we should have a 50% grey value. Okay, you could write in grey, you could write in light grey or dark grey, but you know, I just like to have control over the colours. We need a second line, plt.axh line. We want this at 1.0, and we can basically steal everything that's here, so we don't have to reinvent everything. We've got 2 commas there, and so let's plot this. Let's see what we get out. Hopefully we should get a psychometric function out. We'll see what happens. What's going on? Pro correct. Okay, so that's Andrew being an idiot. That's me. So hopefully you didn't copy me on that one. What else do we have? Pro correct is not defined. Here we go. It's gone onto this screen here, so let me zip it across. Kapow! Here we are. Right. So here is our psychometric function. Let me just shift it away from behind me so we can see here. Okay, we've got a 50% correct at 45. Okay, so that's good. That's what we wanted. Okay, we're going between 0% correct and 100% correct. And so, okay, and we know that the gradient here, or the shape of the curve between the median, the mean, it's normal distribution, so it's the mean up, okay, and the mean down, they're symmetrical. So this is a symmetrical function about the mean, okay? So that's the psychometric function that we have figured out is actually wrong. Because remember, we've got a guess rate and we've also got a lapse rate. So let's get cracking and chuck those on. So hit Q or escape to get out of that. Let's build our actual psychometric function for a 2 alternate force choice task. So we'll come up here, we'll say we need the modified psych function. So we'll go PR mod equals. Now, what do we need to do? Well, we need to start. Okay, so even when our function, okay, when our Gaussian function returns 0% correct, okay, so it comes to 0, we still need to start or offset by our guess rate, don't we? So regardless, we need to start at our guess rate. So we're gonna, and we called the guess rate, remember, gamma. So gamma plus, all right. Now we need to compress our whole psychometric function to the percentage that's left over, don't we? Okay, so we need to go 1 minus gamma, okay, minus lambda. Okay, so this is going to do the compression. This is the bit that's left over. Okay, in this case, it's going to be 100% minus the 50%, that's the guess rate, minus the 5% of the lapse rate. So we're left over with 45%. We're going to have to build our whole psychometric function in the remaining 45% that's left over. Have a think about that and see whether or not that works out in your head, okay? So multiplied by, well, we just multiply it by our normal, our unchanged cumulative distribution function, norm.cdf, .cdf, and we want stimx, mu, and standard deviation, okay? By doing this multiplication here, okay, because remember, hang on, let me just take a step back. This function here is going to return a value between 0 and 1. That's what we showed in our first plot, right? That's the psychometric function. And so if we multiply this number between 0 and 1 with the amount or the percentage that we have left over, all right, that's going to then do this compression, okay, between 0.5 and 0.95, okay, or between gamma and 1 minus lambda, okay? So just have a think about it, play around with it in your head. It's really cool, and I hope it makes sense for you. All right, let's add this to our plot. Stim x. It's still the same x values, but now we want the modified PR mod, okay? And what we can do is we can basically steal the rest of this, Control C, sorry, but we'll change the color. We'll make it blue. Okay, and for those of you who are color impaired, I'll make the markers different for you. Okay, so hopefully what we should see is a second cumulative distribution function that now takes into account the Gaussian, okay, and the lapse rate. Sorry, not the Gaussian, the gamma and the lapse rate. Now I've got an error. Oh, I spelt it wrong. Oh, LMA. That was an error that was waiting to be found, wasn't it? We'll hit the start button again. There's probably many of you going, Andrew, you can't spell to save your life. And I'd say, yeah, I can't spell to save my life. All right, it's come here. Right, there we go. We can now see in the red with the X's, we can see the original psychometric function between 0 and 100%. But now we know that if we run a 2 alternate force choice task with a 50% guess rate, we know that when the stimulus becomes too difficult, in this case it's the orientation becomes too similar, the mouse is going to start to guess at a 50% guess rate. So there we go. Bully for us. We have now adequately taken into account a guess rate. The other thing that we've noticed is that even when it's the simplest task possible, okay, we are still going to get about a 5% error rate. And that's what we see here. Okay, we see this Gaussian drop down by the lapse rate. And so this value here is actually 0.095. And we can see that down the bottom. If we look down here on if you look down here, I don't know if you can see that. When we zoom in on it, you'll be able to see that this should be about 0.95. And it is 0.95. Okay. So this is it. This is a more accurate representation, of the psychometric function for a 2 alternate force choice task. And we have now included guess rates, the lapse rates. And now when you want to start to model your data, you now know, hey, we need to think of, well, is the mouse guessing? What percentage correct would they get correct? What percentage correct would they get when they're guessing? I'm confused. Okay. We need to take into account a guess rate and the lapse rate. The end. All right. I'll leave this video here. I'm now going to stitch these 2 videos together, the whiteboard and this one. If it works, you'll see it. If it doesn't work, you won't see it. But if you do see it, thanks for sticking around. I had lots of fun. And got to think of the next video. See you around.